Hi everyone, welcome back to the Technion CCE Deep Learning course. I'm Tal, and in this video, which is the final part of the sequence modeling tutorial, we are going to cover recent progress in transformers to make them better and faster. You can think of this tutorial as a bag of tips and tricks that make transformers tick, and there is a lot to cover, and new revelations are happening every day. And at the end of this part, I'll tell you about good sources to stay up to date. So let's start. Okay, so this section is called How to Tame Your Transformers, and you will see why in a minute. Now, transformers are notoriously hard to train, as they are sensitive to the size of your dataset and the choice of hyperparameters, including the learning rate, batch size, and optimizer. Now, what we're going to do is I'm going to tell you about a collection of tips and tricks that make transformers much more stable and converge faster. Now, there is a link here to show you. If you want much more details, then you can go to this link, but I'll give you the gist of it in this tutorial. So the first thing we are going to talk about is initialization. Now it matters, especially in large language models, LLMs, and not only for stability, but also for the final performance. So I want to show you an example from one of the early LLMs, which is called Bloom, and they collected the lessons they learned from training big or very large models. And one of the things they discovered is that the initialization had a huge impact on the training stability and also the final performance. So just changing the standard deviation of the Gaussian, where they draw the weights from, and making it much smaller, really improve the stability of the training. So we are going to talk about initialization a bit more in detail, but it's important, and it's also important for other models, not just attention. Okay. Now there are many approaches, but the ground rule is using low standard deviations for the initialization distribution, which is usually normal or Gaussian. Now, GPT and T5 have similar initialization up to small differences in the CDs. So GPT is from OpenAI, T5 is from Google. Now, if you are using PyTorch native implementation of attention transformer models, then it's better to initialize them manually, as the default initialization is usually not good enough. Now, if you are training really large models, or like LLMs, they usually require much more careful initialization, which is depth dependent, so how many layers you used. And there are throughout the recent years, there have been many proposals for kind of special initializations that are not as simple as just Gaussian initializations. And you can take a look at the recent initialization schemes right here, and you can pick something that works for you. But as a ground rule, you can just start with the very simple initializations, which is just initialize with small standard deviation. And you can see an example here. So we talked about initialization in the MLP tutorial. So you remember that the init weights function. So basically we take the linear layers and initialize them with normal distribution with very low, very small standard deviation. And for the others, and the biases, we turn them off, not turn them off, but initialize them to 0. They will be changed during the training. So it's important to keep that in mind. You can start with this simple one, and if things are unstable, you can take a look at the others. Now, another important aspect of training of stability of transformers, is the learning rate and the optimizer. And the reason of the instability are usually because the specific optimizer you choose and because of the normalization you use. So there is a very in-depth analysis of all this stuff, and I'm going to try to give you the gist of it. But if you want to dive deeper, then there are links to the actual papers. Right now, what we can see in this plot here is that we sometimes can stabilize or even improve the training dynamics by not starting with the learning rate you want to, but gradually increase the learning rate. So this is called learning rate warm-up. So basically you will go up, and at some point you will start going down because you're using a scheduler, hopefully. So a paper from 2020 found that learning rate warm-up actually is essential both for RAdam and SGD, and you can see that the loss for when you use warm-up, and the training dynamics are much more smooth. And they discovered that it's important, especially for attention. And the idea is that we are going to gradually increase the learning rate at the beginning of the training. Now, it has some obvious disadvantage for how do you pick this number of warm-up steps. So how long do you have to wait until you reach the learning rate you want to get to, right? Now, let's talk about a bit more why this is necessary and why it's important. Now, I'll just tell you that today we can avoid this by using other kind of normalizations and other kinds of architectures. So I'll talk about it towards the end of this part, but just keep that in mind that this analysis is from 2020 and things have kind of changed since then. Okay. So in 2020 they found out that without warmup the gradients vanish very quickly, and also the RAdam updates rapidly become much smaller. So remember, RAdam is an adaptive optimizer. So and it's adaptive for each parameter. So we have an effective learning rate for each parameter. It was also observed in 2020 that differentiating through the self-attention mechanism create unbalanced gradients. Now, they term it the gradient shrinkage effect, and basically they found that the magnitude of gradient through the layer normalization is inversely proportional to the magnitude of the input. Specifically, they show that they show theoretically that when you differentiate through the LayerNorm layers, the gradients are unbalanced, and consequently, the gradient tends to vanish for lower layers in deep models. Now, combine or couple that with the adaptive optimizers like RAdam, they aggravate the shrinkage effect as the variance of the RAdam update is unbounded at the start of the training. So this is why you don't want to start with a high learning rate at the beginning, right? So this diagram actually summarizes all the theoretical findings. So the two main suspects for the instability are the RAdam and the layer normalization. So let's see what happens. So the layer normalization is responsible for unbalanced dependencies, and it can also cause gradient shrinkage. Now you couple that with the RAdam updates, so the variance of RAdam updates, which are high at the start of the training, they actually aggravate the gradient shrinkage effect, right? So basically gradient vanishing at the lower layers. So lower layers do not change much, so they don't get meaningful gradients. And also there are other reasons for layer normalization to cause issues. And basically they show that when you do learning with warm-up, so basically you gradually increase the learning rate at the start of training, then it can alleviate the effect of this. Now remember that this analysis is true for the post-norm architecture. So what we implemented in the tutorial, where the LayerNorm is after the attention. Okay. Now here is the implementation of a warm-up scheduler. So basically you increase the learning rate at the beginning up to some point, and then you start decreasing. So it's kind of different than what we saw, that we usually set a learning rate and then we just decrease it throughout the training. But now we actually do, in the first part of the training, we increase the learning rate. So it introduces another hyperparameter, which is the number of warm-up steps. Okay, so this is also need to be carefully tuned. Okay. Now, another aspect of the of transformers is the activation. So in what we did, we used just value, but it turns out that there are several. There is a family of activations which is called the gated linear unit family, which actually perform much better. And although it costs us in complexity, if the performance is much better, then it might be worth it. So we can replace the ReLU. We have ReLUs in the MLPs, right? So we can replace them with GLU family, and there are several ways to do it, right? So you can see the functions here, and the most popular one I think is SWGLU. Okay, so SWGLU just implements this. So we use swish and this expansion of the layers. I'll show you in a bit how it is implemented, but there are other functions that also work kind of well. Now, why they improve the performance? So I'll just quote the original paper. So the reason for its effectiveness, so we offer no explanation as to why these architectures seem to work. We attribute their success, as all else, to divine benevolence. Okay, so this is from the conclusion part of the paper. So it works because it works. Okay, so here is an example of SWGLU. So it's a bit more expressive. So we add another layer here, and you can see that the one line that is replacing the one line from before. So just swish instead of ReLU, and also this multiplication here, right? So this is the equation from this part. So we can see the comparison between the different activations, and you can see that the GLU family is usually much better than just using ReLU or just using GLU. Okay, but you can see that it's usually not that of a large margin. Okay, so it's kind of close. So if you want to add like 0.1% to your performance, then just replace the ReLU. Okay, so this analysis of the gradient vanishing and things like that, it's usually because of the layer normalization, and the position where you put layer normalization has a great effect on the outcome. So let's see what are the alternatives to this layer normalization and which one works the best. So as the problems we introduced above are directly connected to layer normalization, it is natural to question whether we can train deep transformers without it or with some alternatives of it. So indeed it's possible. Sometimes we can achieve even better generalization without layer normalization, and I'll show you a couple of approaches that people are doing, and you can pick whatever works for you. And the main concerns are, of course, the final performance and the stability of the training. So if the training is very unstable, then maybe you have a lucky seed and get really good performance, but if you run it again, then it's unstable, it will diverge, and you don't want this kind of model. So the first thing to do is just to change the position of the layer normalization. And actually, this is what people do today, especially in GPT architectures. It works really good, and this makes us not need the learning unit warmup, and it works really well. So my recommendation is just to start with it. So if we want stable learning, just change the position of the LayerNorm, and the idea is that to put it before the attention. So this is why it's called pre-norm. So what we introduced above was post-norm. So this is the top architecture here is the post-norm, what we implemented above, right? And pre-norm means just move the LayerNorm a step backwards, right? So the LayerNorm goes before the MLP and the attention. Now it's very easy to implement it. So here is the encoder from before. We just move the position of the LayerNorm, okay? And this works much better. Maybe sometimes not much better, but very close in performance to post-norm, but it's much more stable, okay? So I recommend just start with that. And in the native implementation of PyTorch, just use norm first equals true, okay? So this just pre. Another trick is to remove LayerNorm at all and don't use LayerNorm at all, and this is called ReZero, okay? And the idea is that to have some learnable parameter here, which is initialized to 0, and this will help us take care of the scaling, okay? And basically, it's very simple modification. So this is just a learn parameter, which is is positioned right here instead of the LayerNorm, and this is like the post-LayerNorm architecture. It's very easy to implement as well. So instead of LayerNorm, you have a trainable weight, right? And just replace the post LayerNorm with ReZero. Okay. Now, which one works better? So first of all, when you use ReZero, it's less parameters, so just single parameter. And here we have in LayerNorm we usually have the shift and bias, right? The shift and scaling, right? And we will see in a minute a table where we can see which one works better. So what else can we do? So we had prenorm, we had ReZero, and we now have SandwichNorm, which is just, why not do both prenorm and postnorm? So the idea is just put LayerNorm before and after. Okay. Now the graph here shows that it works really well, and it also, this graph shows you the magnitude, I think, of the gradient of the final embeddings size. So basically, it shows that the size of the embeddings does not grow too much. Okay, which is of course important for stability. So this introduces more parameters, of course, right? Is it used today? So it's a good question. I think there was one recent model that used it, but it's more popular to use just prenorm. Okay. Now we can use prenorm, but we can just replace the LayerNorm with something else. So a recent normalization is called RMSNorm. It's much faster than LayerNorm, less parameters, and it works really well. So RMSNorm just doing this function. So we take the input, we normalize it by the size norm, by the norm, and then we have this scale parameter which is learn. So it's very easy to implement. So just replace LayerNorm with RMSNorm, and it works really well. Okay. So you can see the implementation here, and this table summarizes all the improvements. So RMSNorm works in the prenorm. So you can, of course, you can do this in postnorm, but usually people do prenorm, and we can see that it works kind of well. Of course, everything is closed, so don't be too surprised, right? And these are just little tricks to improve the speed, stability, and performance. Okay. Now, another approach would be to, if we talked about RAdam and we thought that in the postnorm architecture we need to warm up the learning rate, then it was found that the high variance of learning rates in RAdam at the early stages of learning is due to the lack of samples in the early stage of learning. So since we are working on batches, right, and on many batches, and we don't see the entire data, then there's high variance in the gradients, right? So they did an experiment which shows that this is actually the cause, right? So the lack of samples, right? So they just introduced a modification to RAdam, which is called Rectified RAdam, where they wait with the variance updates. And basically, they gradually change the momentum term over time in a way that helps to avoid high variance. Okay, so we can see the graph here that when you do RAdam with Warmup, it's good, and when you use RAdam, it's good, but when you use just RAdam vanilla, it's not good. But this is mostly true for the post-norm architecture. So for the pre-norm, you don't really need a rectified RAdam. So our RAdam is implemented in PyTorch, just replace RAdam with RAdam, and nothing here too special. Now the final thing we are going to talk about is the positional encoding. So we talked about them, and we know that they are important when we need to embed the positional input. So this is true, for example, for sentences in NLP, or the time embedding for time series and things like that. And we did something very simple. So we saw the sine and cosine ones, which are static, not learned. We also saw the learnable positional encoding, which is what's used in GPT. So it's very simple to implement, but it adds more weights. Not very, like, it doesn't have a huge impact like the number of layers or heads, but but it really much easier to implement it than the cosine and sine one. Now, there is a great literature that deals with how you embed a position. So what we actually did is called absolute position bias. So basically, for each position in the input embedding matrix, we gave it a unique indicator, a unique value. So I hope you remember that. But we can do something else, right? We can actually do something called relative positional embedding. So instead of encoding the absolute position, we can encode the position which is relative to something. So here we can see that for each input in the sequence, and we encode the other entries in the sequence with respect to it. So for the first word, so you are great. So the attention matrix, which looks something like this. So the positional embedding, the relative one, will be R0. So U with respect to U. U with respect to R. So we have a relative embedding which is +1, and U with respect to great, which is +2. So we actually have an embedding for the relative position. Now we can do this for every entry. So if we look at the second word, so R, so we can see that the U is now -1 with respect to it. And of course, these are learnable, and it sometimes work much better. And it makes sense, especially if there are physical attributes or things like that. Right? And we directly inject the positional embeddings to the attention bias. So instead of adding this embedding at the beginning, so remember we had tokens, we converted them to embeddings, and then we added the positional embeddings. So here we just convert to embeddings. No, we don't add the positional embeddings before the attentions. We add the positional embeddings to the attention matrix. So we calculate the attention and we sum it with the positional embedding matrix, which is relative. Okay, so there is a great literature on this. So it's termed RPE, relative positional embedding, and there are many ways to do it. So the very simple one is just learn it. So this is T5, what it's doing. But we can also have other constants, which can help us with interpolation to much larger contexts. So, for example, there is something called alibi, and also a rope. So basically, the idea is like this, but instead of learning them, we can actually predefine the rules how to calculate them. And we can see here some code examples, so how to implement them. So the implementation is quite more complex than the simple one, but for several applications and the most recent LLMs, large language models, they use this kind of position. I think the rope is quite popular. So rotary positional embeddings. Okay, so that was a lot, and it's only the tip of the iceberg. There are many more. So how do you stay up to date with all these improvements? So there are a couple of repositories that are constantly updated. So for example, I like this one, so X transformers. And you can see here all the type of improvements that are implemented here. So it's very long. Okay, so you can see it's divided by sections, and you can see what is the goal of the improvement. There are other ones from Meta and from Microsoft, so check them out. But I think X transformers is pretty good. And you can take a look if you want to solve something with transformers. So that's about it for the sequence modeling tutorial. Thank you for watching, and I will see you next time.